Yeah.
I don't know if that's good.
With grades. Yeah, so, I didn't know it. I think they feel like all kinds of stuff, like, artists have heard. Yeah, they go for results and ideas. Yes. His name was like, it was all. Ask her. Oh, okay, well, right. Yeah.
No, I'm just saying like. Is that audio? Now, audio is just going.
What?
What you're talking about.
You went to Oregon? No, he didn't.
You know, it's okay. Because I remember the.
Okay, guys, page 9.
Begging. You fought us to meet. Oh, I God, you did. Oh, wow. This would be out. You're like, it's just fine. Yeah, with us. You have 9/11. It's 9/11. Oh, yeah. You sound. Yeah. Today's like exactly the day. You did do that week before? I'm not. That means it's not even us. We don't actually.
Okay, so I think we started example 1. Anytime that there is a word involving rate, we know there's going to be a time component for our derivative. So a becomes dA dt, x squared becomes 2x, and we also need to attach a dx over dt. So we can start plugging in, right? So we can replace dA dt. That's the variable we're looking for. X gets replaced with 15, and dx dt gets replaced with 5. So we multiply this through, we get 150. And then our units of measure, area is centimeters squared, and then time is minutes. So we divide them by each other. A couple things to point out. If you see the word increasing or decreasing, that is going to impact whether you assign your rate as a positive or negative. So if your rate is decreasing, then you want your rate to be negative. If your rate is increasing, then we want our rate to be positive. And since the sides of the square are increasing at 5 centimeters per minute, it should make sense that the area is also growing with a positive rate. If you're ever struggling to figure out what the units are for your variable, or for your variable, look at the variables involved. So area, find the units for that, which is centimeters squared. Look at time. Time is in terms of minutes, so we just divide them over each other, centimeters squared per minute. All right, example 2. 25-foot ladder leaning up against the vertical wall. The bottom of the ladder is being pulled horizontally away from the wall at a constant rate of 3 feet per second. How fast is the top of the ladder moving? And in what direction when the bottom of the ladder is 15 feet from the wall? So go ahead and we're going to draw our diagram. We have a ladder leaning up against the wall, and the ladder is getting pulled horizontally away, which means that it's dropping down as well. Now, what we're concerned about is the sides of this triangle that's changing, right? So we can imagine that the shape of this triangle is changing as the ladder is dropping. So we can expect this, it'll stay a triangle the entire time. But this base length is increasing over time. We can expect this vertical distance to be decreasing over time. So we know that this problem is kind of focused around the sides of this right triangle. So I'm just going to go ahead and label them as X, Y, and Z. And the equation that's going to relate these three variables is going to be Pythagorean theorem. So we're going to build out our equation. Our equation is a squared plus b squared equals c squared, but because of the variable that I'm choosing, we're using x squared plus y squared equals z squared. Okay, so we go ahead and find the derivative. I like to find the derivative first. It just gets out all the variables in front of us so that we can see so we can begin to assign these variables with values. So every variable just gets impacted by time, but all these variables are just power rule to find the derivative. So x squared becomes what? 2x. And because we're asking for x's derivative with respect to time, everything is being impacted by time. We will multiply this by what? dx over dt. Yeah. Okay. We go down the line. Every variable, power rule, and then we attach a d over dt for that variable. We have 6 variables in front of us. Let's just identify each of the 6 variables. If you can save a little bit of room on the right side here, there's going to be a part B that's going to be asking about the rate of change of area. So just see if you can save some room there. All right, so let's reread the problem and see if we can start assigning values to these variables. 25-foot ladder is leaning up against a vertical wall. So we're going to put that 25. See, okay. The bottom of the ladder is being pulled horizontally away from the wall at a constant rate of 3 feet per second. What do you think this 3 is going to relate to? Yeah, so anytime you see anything with rate, anything involving time, you see the word rate, pulled, all these motion words, you know it can't be a static value, it has to be a rate. And it's horizontal, so we know it's going to be the rate of change of that x, and it's going to be 3. Is this going to be a positive or a negative rate? Positive, because what's happening to x? It's growing, yeah. So I want to point this out because I drew this triangle in this way because I just want to students to see that a lot of times we associate left with negative and right with positive, or we associate up with positive, down with negative. In this case, the direction is not going to matter. What's going to matter is what is happening to that length. If that value you're talking about is growing, that's deciding whether the rate is positive. Okay, if that length is decreasing over time, that rate is negative. Could be moving left, could be moving right. We don't want to associate direction with sign. So just want to make that clear. How fast is the top of the ladder moving? All right, so what variable do you think that's referring to? Yeah, dy. We know we're talking about a rate. We're talking about the top of the ladder. We're talking about this vertical movement. So the dy dt is going to be the unknown that we're looking for. when the bottom of the ladder is 15 feet from the wall. What variable is that? X, yeah. So this is a static value. There is no rate involved. We know the bottom of the ladder, 15 feet, that's going to be involving X. So the hope is that we can solve for dy dt, but to solve for dy dt, we would like the rest of these 5 variables to be filled with numbers so that we can solve for that variable. So right now we don't have enough to fill in, but I think we can use context clues to kind of figure out what y and dz dt are. So y is the length, the vertical length of this triangle at this moment in time. Well, if I have 2 sides of a right triangle, can I find the third side? Yeah. So Pythagorean theorem, right? X squared plus y squared equals z squared. So plug in 15 in for x, plug in 25 in for z, and solve for y. Again, you can use your calculator in this unit, but if you can recognize this as a version of the 3, 4, 5 right triangle, then we can see that y is just going to be what? Yes, it's just a variation of 3, 4, 5 right triangle. It would be just 20. But if you didn't know that, it's okay. You can just plug in the calculator and confirm that your y is 20. Okay, the other thing that's missing is dz dt. So dz dt is talking about the rate of change of the z length. So the z is talking about the ladder length. Is this length is starting at 25 feet. Is this length going to change over, okay, it's going to drop, but it's going to stay 25 feet the entire way through. And because of that, what do you think your dz dt will be? 0. Yeah, that rate of change is never going to be different, right? It's going to be 25 at the beginning, 25 at the end. There is no change. So there's no change. It's going to be 0. Now, we're going to see different variations of Pythagorean theorem problem. Not every problem is going to have a dz dt of 0. It depends on how the triangle is changing. It's just that for this problem, we can safely say dz dt is 0. But for every problem, we kind of have to imagine the problem in motion, and then as we imagine the problem in motion, we can decide, use what we can visualize to make some of these assumptions. Okay, everything we need is in front of us. We can plug in for all these variables, and then the only missing variable that we're looking for is d by dt, and we should be able to solve that since we have something for every variable. Okay, try that. You can plug everything. Oh, and then by the way, when we solve for dy dt, we haven't solved it yet, but what sign would you expect out of dy dt? Negative. Okay, why is that? Good, it's decreasing. Not because it's going down. Sometimes going down may cause something to increase. So again, don't associate direction with sign. Look at your value. Is your value getting smaller or is it getting larger? Here we can visualize that the y is getting smaller. So that's going to help us decide that, or to expect, sorry, that dy dt is going to be negative. So when I cleaned everything up, I got -9/4. What is our unit of measure going to be? And again, if you are not sure, look at your variable and look at what each of the units variables are. So y is in terms of what? Feet. Time is in terms of, yeah. So that's going to be your units. Okay. So feet. Oops, sorry. Okay, any questions with part A? Part B says, at what rate is the area changing? So now we're talking about the rate at which the area is changing. We see the area in front of us is a triangle. Before we can find the rate, we have to first create the equation. What is the formula for area of a triangle? Okay, yeah, 1/2 length or base times height. Yeah. In this case, if we just want to adjust our equation, our formula with the variables that we're using already, because we can reuse a lot of the data from part A in for part B. So we know the area is just 1/2 base, which is x, times height, which in this case is y. Okay, we're looking for the rate of change of area. We're looking for dA dt. So we can just go through our derivative process. But to find the derivative, what else is needed? Can I just say that the derivative is 1/2 dx dt times dy dt? We got to go through what? Product rule. Yeah. So anytime you have two variables multiplied together, we do have to involve product rule. So I'm going to assign my f to be 1/2 x, and then my g to be the y. All right. Remember, we're still under related rates, so every variable is still going to get impacted by time. So what's 1/2 x's derivative? Yeah, the 1/2 is going to stay, and then x goes to 1, but we are going to have to involve dx dt, so 1/2 dx dt. Okay, g, that's the y. Now, do we include dy dt here? No, why not? Okay, not a derivative, right? So we only are going to involve dx dt or dy dt if something is asking for the derivative. If something is not asking for the derivative, then we shouldn't have a derivative variable show up. Plus f back to 1/2 x. Now g prime becomes what? dy over dt, yeah. Now this is talking about the same moment in time, so all the data that we gathered from part A can be plugged in. So we can replace dx dt with 3, replace y with 20, replace x with 15, and then replace dy dt with -9/4. We can plug into our calculator. You can leave your answer in decimal value, that's okay. The thing I want to talk about here is, what do you expect the units to be, though? Good. So we look at each of the variable. Area is feet squared. Time is seconds. So we just put them over each other. Feet squared per second. All right, let's look at page 10. Okay, a spherical balloon being inflated at a rate of 10 cubic centimeters per second. Find the rate of change of the surface area of the balloon at the moment when the surface area is 64 pi. Now, as far as geometric formulas go, the only ones that I expect you to know, as well as College Board, is just the basic ones. So Pythagorean theorem, you need to know that. Area of a square, you need to know that. Area of a rectangle, circumference of a circle, circumference of a circle, area of a circle, right? Those are basic ones. We should know that. And all the other formulas, like volume of a sphere, a cylinder, all that, those will be provided for you. Okay, so I'll give them to you. College Board will give them to you. So don't have to worry about, the complicated geometric formulas. But, the big ones, rectangle, square, circle, area, and circumference, we need to know those. Okay, so these will be provided for us. We have volume of a sphere, which is 4/3 pi r cubed, and surface area of a sphere is 4 pi r squared. Let me read this again. A spherical balloon is being inflated at a rate of 10 cubic centimeters per second. Find the rate of change of the surface area of the balloon when the surface area is 64 pi. We know we have to involve derivative because we see rates involving volume. We see rates involving surface area. So I'm just going to go ahead and find the derivatives, and that way we can just have everything, all the variables showing in front of us. Remember pi, treat pi like you would a coefficient. The only variable that you see here are v and r. So these are the only ones that will get impacted by time. All we need is power rule here. Same thing here. All we need is power rule here. There's no need for product rule. Pi is not a variable. It's just a constant. Okay. So let's just find the derivative here. So v becomes dv dt. We do power rule, bring down the 3. The 3 cancels out with this 3 in the denominator. So I'm left with 4 pi r squared. I just asked for r's derivative, so we need to include what? dr dt now. Let's go ahead and just find the derivative of s. S becomes ds dt. 4 pi r squared becomes times dr dt. Okay, let's list out all the information in front of us, and then we can see, how can we use these combination of these 4 equations to help get us to our answer. And it may require us to use a couple of them. We may not have to use all of them, depending on what the problem says. Okay, so a spherical balloon is being inflated at a rate of 10 cubic centimeters per second. Can we identify what variable that could be referring to? Yeah, so sometimes if you're having trouble deciding, what value or goes with what variable, look at the units. The units is a lot of times going to help you decide. So you see cubic centimeters, it has to be something involving volume. But then you see per second, so it has to be a volume with time in it. So it has to be dv over dt. So we know that dv over dt will be 10. And then can we assign this to be a positive or a negative 10? Positive, because yes, it's increasing, it's being inflated. Whenever the problem gives you a rate, they'll give you context clues, but they won't tell you whether it's positive or negative. You're going to have to be the one to decide whether to assign that rate to be a positive or negative. So positive 10. Find the rate of change of the surface area of the balloon. What are we looking for? Yeah, dx over dt. You see surface area, but then you see rate of change. So, it has to be a moving component of surface area, so it has to be ds dt. So that's our goal. Our goal is to look for ds dt when the surface area is 64 pi. Yes, okay. Okay, let's start at the end. Because if we can plug everything in at the end, then we don't have to do a bunch of work here. So we're looking for ds dt. So ds dt requires r and dr dt. Do we have either information? No, but we have something related. Maybe we can use these to help us get to where we want to go. So first, how can this surface area equation help us out? Or sorry, surface area value help us out? Yeah, plug it into S and then solve for what? R. Okay, so that's one piece of the puzzle. And we can solve for R. Okay, so that can help us get to R. But we're still missing dr dt, right? How can dv dt value help us out? Yeah, plug it, dv dt, replace it with 10. And by this time, we should have R figured out, plug the R that we found from our surface area, and then we should be able to isolate dr dt, and then that should allow us to get us enough information to plug in and solve for ds dt. So we're just kind of going around and working each of the equations to get the information that we need. So I'm going to start here, 64 pi, plug it into S, solve for R. That's one piece that I need. So now that I have R, I can use these two pieces to help me get to dr dt. That's the other piece that I know I need. Right? What will we do to divide to solve for dr dt? Oh, yes. Oh, sorry, squared. Thank you. Ends up being 64. Sorry. Okay, what would you do from here? Divide. Okay. 64 pi. So dr dt. You can leave that alone, or you can reduce. If you reduce, it'll just make it easier to plug in. So I can take the 10 and 64, make it 5 over 32. All right, everything that we need is in front of us. We have R equals 4. We have dr dt is 5 over 32 pi. And then all of this can be inserted into ds dt because that's our goal, right? We're trying to find ds dt. So replace R with 4, replace dr dt with 5 over 32 pi. And then we can solve for ds dt. 8 times 4 is 32. The pi's also cancel out, so the only thing left is what? 5. And then we got to worry about the units. Right? So let's look at our two variables here. S, surface area. What's the unit for surface area? Good. Yeah. So we know it's going to be centimeters squared. Surface area, if you think about the word area, that's a two-dimensional unit. So centimeters squared per second. I do want to point out a trouble spot that students experience when they do reducing here. I think whenever we see pi, I think our tendency is we're more used to seeing pi in the numerator, right? So if you're dividing by that 64 pi, that pi needs to stay in the denominator. But I see some students, they see that 10 over 64 pi and they assume that the pi is the same if they just brought it up. So they bring it up to the top, make it 5 pi over 32, but then that's different value. So just be aware that if algebraically, if the pi ends up in the denominator, it needs to stay in the denominator. Otherwise, you're changing the value of your value of your fraction. Okay. Any questions? Okay, let me skip 4 for now, and let's look at number 5. So number 5 is a cone problem, and cone problems require similar triangle, and it's the most it's like the most algebraic intensive of these problems. So we'll get practice with a couple of these. But any questions with number 3? All right, let's look at number 5. Cone has a volume formula, which will be provided for you. Okay, so V equals pi over 3 r squared h. A cone, vertex down, so we have the pointed end below, 10 feet across, and 12 feet deep. If water is flowing into the tank at a rate of 10 cubic feet per minute, find the rate of change of the depth of the water when the water is 8 feet deep. So let's list out all the variables that we see, all the values for variables here. So we have the dimensions that we see here. Water is flowing into the tank at a rate of 10 cubic feet per minute. What can we assign the 10 to be? 10 cubic feet per minute. Yeah, volume over time, so dV over dt. Okay, so dV over dt. Positive or negative? Positive, right? We can, as water is flowing into the tank, we expect the volume to be growing over time. So positive 10 cubic feet per minute. Find the rate of change of the depth of water. What variable is talking about the depth of water? Yeah, so expect dH over dt. H is the depth, and so rate of change will be dH dt. That's the unknown. When the water is 8 feet deep. H, okay. So H is 8 feet. Okay, put a star next to, or put a star next to the 8 feet. This can distract us because we're going to use it, but not until the end. Okay, so do not use until the end of the problem. I'll show why some students want to involve that 8 a little sooner than we need it. Okay, so the issue is that as water is coming to the tank, the radius, okay, so we have a cone within a cone. So there's a cone created by the tank, but then there's also a cone that is created by the water that's shaped by the tank. So there is a cone within a cone. And so this formula for us is really referring to the what's in for the water inside. So as water is coming in, what's happening to the radius? Is it staying constant or changing? Changing, right? So as water is coming in, we expect the radius to be growing. What about the height? Also growing. So we have two variables and not enough information. So what we need to do is we need to replace one with the other. But to do that, we need to be able to create a relationship between the radius and the height. So what we're going to do is we're going to think of this as a similar triangle. So if we just look at this portion of the diagram, okay, we're just looking at that portion of the diagram, and we're just going to label our parts. So what this is now going to be representing the radius of the container. What's the radius of the container? 5. Okay. The height is still going to be 12. But we know that as water is coming in, the radius and the height of the water level is changing, right? So these we have to leave as variables. All right. Good so far. Now, is the height changing as time passes? Yes. But I think what sometimes students want to do is they want to start involving the 8 in for the h. But if you involve the 8 in for the h, then you're saying that the height is staying constant at 8 the entire way through, which we know is not the case. So once we get our derivative established, then we can use the 8 to help solve our problem. But we don't want to use the 8 too soon, because if we do, we're kind of changing the overall process of this problem. So we are going to use it, but not yet. We want to hold on to that h until after we build our derivative. Okay, so using similar triangles, using proportions, we can say this. We can say the radius of the small cone is to the radius of the large cone, as the height of the small cone is to the height of the large cone. So we're creating proportions. We have a triangle within a triangle. We know that these values are proportional to each other, so we can create this portion. Okay, next up, let's cross multiply. We still don't know what variable to solve for, but I just want to get the fractions out of the way. So let's say we have 12r is equal to 5h. So the reason that we're doing this is we're trying to get our volume down to just one variable, either r or just h, so that we can find the derivative because we have too many variables and not enough derivative information. But the decision is, what variable do we want to solve for? Do we want to solve for r, or do we want to solve for h? Now, either one is okay, but one of them is going to allow us to get to our answer faster. The hint is looking at what data they're asking for, and also what data is given to us. So if you look, everything here is in terms of h. So we would prefer to have h as in our equation, which means that we would like to replace r. Okay, so if I can replace r in terms of h, then everything in terms of h, our derivatives in terms of h, and then these will just naturally show up for us. So our goal is trying to find a replacement for r as we make our substitution. So if we want to find a replacement for r, I want to solve for r so I can replace my r variable. So if I solve for r, I can divide both sides by 12. I get 5h over 12. So now this is going to be my replacement to put in for r in terms of h. So I'm going to update my volume equation. and put the 5h over 12 in for the r. So v is equal to pi over 3, 5h over 12 squared times h. Okay, questions so far? The only derivative rule we need is power rule. So we shouldn't have to do a whole combination of product and chain. We should be able to clean this up so that the only thing we need is power rule. So spend your time to clean this up. Your derivative should be an easy process. It shouldn't be a complicated process. So I'm going to try to expand or clean all this up. So I can square the 5, square the h, square the 12. And I want to merge the variables together, put the coefficients together as well, so that my derivative should be an easy process. 3 times 144 ends up being 432. So if I just push the coefficients in front, and then there's h's that I can merge, right? H squared times h is h cubed. So I want to get to this stage before I apply derivative. But once you get to this point, it should be a relatively easy derivative process for us. Okay. We just have to do power rule for both these variables. Okay. So any questions from here to here to here? All right, so now let's find the derivative. Okay, so v becomes what? Yeah, dv over dt. Anything happen to this? No, it stays, right? That coefficient stays. So 25 pi over 432. The only derivative we have to worry about is this h cubed. H cubed becomes what? 3h squared. Now we're asking for h's derivative, so dh dt. All right, so now everything, we're almost done. We just have to be able to solve for dh dt. We have everything that we need. Replace 10 in for dv dt. Replace 8. Now we can use the 8. Replace 8 in for h. And then we can now solve for dh dt. Okay, so. Now, as you use your calculator, we want to present our answer as an exact value. So don't plug pi in the calculator. If you plug pi in the calculator, it's going to return you 3.14, and it's going to give you a decimal value. I think maybe with the 36 Pro, it may hold on to that pi value for you. But for now, in a sense, kind of treat pi like a variable. So just move it where it needs to go, and then you can plug the rest of the numbers in the calculator, but just leave pi out of it just so that you can maintain an exact value. Dividing by this fraction is same thing as multiplying by the reciprocal on the other side. So okay, where do you notice pi end up being? Denominator. So when everything is said and done, we do need to make sure that pi stays in the denominator. Yes.
What is the
Because this is just a number. So imagine if it was just like v is equal to 4h cubed. The derivative would just be, you keep that 4 there. So I know it looks messy, but it's just some random number that's sitting in front. So if you multiply the 10 times 432 divided by 4,800, it should get you down to 9 over 10, and then just keep that pi in the denominator. And then our units of measure. This is dh over dt that we're looking for. So height is in terms of feet, and time is in terms of minutes. Yeah, so it's going to be feet per minute. Okay, this problem is pretty labor intensive, but we'll get a lot of time to kind of practice through these types of problems.
When we're plugging in that A for H, we only plug it in after we like get
Yeah,
that derivative.
Right, good. Yeah, after the derivative, because if we plug in anytime before the derivative, then we're saying that this is not changing, which is not true. So yeah, this is only after the derivative, not the change.
Okay.
Guys, I'm gonna adjust the homework here. Your homework. Your homework is page 15 and 16 all. I'm jumping because we haven't done other types of problems yet. So we're just going to focus on the problems that we've done. So page 15 and 16, I'll send out a reminder. And then, you can also find the key on my website.
Sorry, like.
Thank you.
Wait, what are they doing?
Their parents are like.
I want to know more. Say, guy.
You know who they were?
I grew up with them in my sister.
Yeah.
Breaking those down. I know why.
I'm like, you know? It's like respect.
Oh, duh.
There you go.
Like, I don't know.